All right.
When put underneath tensile strength,
I'm sorry?
under tension,
Mhm.
pulling, it generates heat, right? It can, depending on the
Well,
materials.
all right, so you put potential energy in the body, and when you let go, yes. So there's potential energy got converted to kinetic, and then eventually.
I used to work at a steel factory, and we would sometimes stretch steel.
Mm-hmm.
If you touched it right afterwards, depending on force, it would be hot.
Yeah, and the more you do it, the hotter it gets. You know, a lot of times, so you're stretching it quite a bit.
We would camber beams, so like something for parking garage, right? Like a parking garage.
Okay.
We would take big I-beams, huge I-beams, and put them in a machine to camber them, which basically puts a pitch on them. So when you lay them on a structure, they hold more of a load because they're already bent upward.
And so now the stresses are compressive stresses.
Yes.
So that's why you build, if you have like canyon walls, so this is a top view. So here's canyon walls, and here's the water pushing you guys, and so this is compressive forces on the walls. So that's why dams are built. So the same thing with beams. Yeah, so the thing to remember is structures are stronger under compressive forces, and you just you use that fact in designing your structures wherever you want to do. Yeah. All right, so let's do a few problems. Okay, first we'll do static equilibrium problems. Okay, so what I'll do is I won't do all four. I'll do this one and that one. Okay. So this one is similar to that, except that this is slightly more complicated than that. Okay. All right, so what's our goal here? Okay, we don't want this thing dropping. Yep. So you're hanging up a sign or something like that. Okay, so let's look at this knot. If you don't want this dropping, this should be at rest. Okay. If that's at rest, now that's a point object. So for that to be at rest, all you have to do is you just got to make sure that this is true. And you don't need a torque equation. Yeah. So let's look at all the forces on that fellow. Okay, so I'm going to draw. So this is the point object, and again, my x and y axes are always like that. If I don't draw them, that's so the tension in this cable is pulling this guy in that direction, and the tension on the wall is, the tension here is pulling the wall this way, but we're not worried about the wall. Right now we're just worried about this guy. So there's the tension T1. There's the tension T2. Okay. The tension in this cable is pulling the weight up and pulling this guy down. And okay, so the tension T3 is supporting the weight, so tension T3 is equal to the weight of the object. All right, so now all you got to make sure is that since you don't want this knot to move, these three forces add up to 0. Okay, so T1 plus T2 plus T3 equal to 0. Okay. That angle is 45 degrees, so this angle will be 45 degrees. All right. All right, so the x component of this is balancing that. The y component of that tension is balancing T3. Right? All right. All right, so let's write the x component of the force minus T1 plus T2 cosine 45 equal to 0. So T2 equal to T1 divided by cosine 45. And 1 over cosine 45 is 1.41 T1. So what we have found is T2 is, this tension is 40% greater than this tension. Okay, so if this tension is 100 pounds, this is 140 pounds. Yep. Now let's calculate. So let's look at the y equation. The y equation is T2 cosine 45 should equal T3 minus T3 equal to 0. T2 sine 45 minus T3 equal to 0. So T2 equal to and sine and cosine 45 are the same, so 1.41 T3. All right, so what we found is, okay, T3, and from this equation you can see that T3 and T1 are the same. All right, so this structure is, here's the weight you've suspended, mg. The tension here is mg. And the tension here is 1.41 mg. Okay. Now, so here, by hanging it like this, now you need a cable that is 40% stronger than the weight you're supporting. So my question to you is the following: why not just hang it right like that, like that? This is just a cable that needs to be mg. You're wasting extra money by putting this structure. What's the benefit?
It's stronger?
Less wiggle. So this is more stable. Okay, so that's why you were willing to spend that extra money. You know? Again, so did you guys understand that? Yeah. So there's always a good reason for doing stuff. Okay. Now we'll do this one. Okay. Okay, again, we'll look at that knot. The three forces are T1, T2, and T3. T3 is equal to mg. Okay. Everybody understand this? So T3 is pulling on the knot like that and holding up the weight, and this tension is equal to the weight, mg. So T3 is equal to mg. All right, that angle is 45 degrees, so this angle is 45 degrees, and this angle is 60 degrees. Okay. Again, you want the knot to be at rest. So T1 plus T2 plus T3 should equal 0. T1 plus T2 plus T3 should equal 0. Okay. So let's look at the x component of the forces. T3 doesn't have x component, only this guy and this guy are balancing each other. Okay. So minus T1 cosine 60 plus T2 cosine 40 equal to 0. Minus T1 cosine 60 plus T2 cosine 45 equal to 0. Okay, so T2 is 0.71 T1, 70% of T1. Yeah. And so this sort of makes sense. This guy is supporting most of the weight, yeah, and this guy is supporting less. Yeah. And if you look at the Y components, so T1 sine 60 plus T2 cosine 45 minus T3 equal to 0. So T1 sine 60 plus T2 sine 45 minus T3 equal to 0. And T3 is equal to mg, the weight you're supporting. Yeah. And T2 is, so T1 sine 60 plus T2. T2 is 0.71 T1. Okay, so let's see how much does this work. All right, so the advantage of this structure, the advantage of this structure is, okay, so you can support this weight with cables. That cable only has to be 60 times as strong, 60% strong, and that cable is even less strong. So with two weak cables, you can support a weight, a larger weight. So if you have a weak threads and you want to support a weight, you put a hook on there and then use cables like that. Okay. And it'll probably work out that the forces would have to be the smallest if the angles are 45 degrees. Okay. You guys can work that out. All right. Okay. A small SUV, 1,000 kg SUV, has a wheelbase of 3 meters. If 60% of its weight rests on the front wheel, how far behind the front wheel is the wagon's center of mass? Okay. Wheelbase is 3 meters, so okay, so this distance is 3 meters. There's the center of mass. Okay. 60% of the weight rests on the front wheel. Okay, so this is 0.6 mg. There's mg. And this is 0.4 mg. Okay. And the way I found that is those are the only forces acting on this object. And so here is mg acting. This is 0.6 mg's. It's not moving. Some of these forces have to be 0. So that plus that cancels that. Okay. Now to find the center of mass, okay, is the object rotating? No, it's not. So let's calculate the torques about this point. Okay. So this distance, let's call it x, and this would be 3 minus x. Okay, so if you calculate the torques about this point, about the center of mass, this force is trying to rotate the SUV counterclockwise. This force is trying to rotate the SUV clockwise about that point. We'll calculate the torque. And since it's not rotating, the counterclockwise torque is balancing the clockwise torque. And we're going to calculate the torques about the center of mass. Okay. And counterclockwise torques are taken to be positive. Okay. So again, you use your right hand, your fingers point in the direction of the rotation, your thumb points in the direction of the torque. So the torque is really coming out of the sheet of the paper, and so that's the positive z direction, and this torque is going into the sheet of the paper. Okay, so that's where the signs are coming from. All right, so the positive torque is the force is 0.6 mg times x is the moment arm minus 0.4 mg times 3 minus x equal to 0. Okay, so you can see that mg cancels. So what you have left is 0.6 x minus 0.4 times 3 is 1.2 plus 0.4 x equal to 0. X equal to 1.2. So the center of mass is 1.2 meters behind the front wheel. Okay, and that's because the engine is there. Had the weight been equally distributed, then the center of mass would have been right in the middle. It would have been 1.5 meters behind the front wheel. So if it was a rear wheel drive, the center of mass would be closer to the rear wheel. Okay. Any questions on that? A uniform plank rests on the level surface as shown below. The plank has a mass of 30 kgs, so roughly half your weight, and is 6 meters long. Each of these tables are about 3 meters long. Again, the front row. So 6 meters is 2 of these tables. How much mass can be placed on its right end before it tips? Okay, so you want to place a mass here, and it's just ready to tip. Okay. All right, so what is this mass trying to do? It's trying to rotate the plank about this point, about the edge. It's trying to rotate, tip it like that. What is stopping it? What is preventing it from tipping? Yeah? Yeah, so the center of mass of this guy is over here. The weight of this guy is preventing it. Okay? So, you guys understand, the closer this guy is to the edge, the lighter the mass will tip him over. Okay? And of course, and when this guy is right on the edge, when the center of mass is on the edge, the limit is 0 mass will tip him over. And when this right edge is on the table's edge, how much mass will tip him over? An infinite amount. Nothing can tip it over. Okay, so those are the two limits. Okay. All right, so this says a uniform plank that's 6 meters. This is 4.2 meters. The center of mass is at 3 meters, so this is 1.2 meters. Okay, and this is mg. capital M for the mass of the plank, and this is, okay? So this force is, we are calculating the torques about this point, and this force will have a clockwise torque. This force will have a counterclockwise torque. Okay? So clockwise torques are negative, minus mg times 1.8 meters plus mg times 1.2 meters equal to 0. Okay, so the mass is 2/3 the mass of the plank. Okay, so 20 kg mass will tip the plank over. Okay, so again, if this was some kind of application in a warehouse, if you want to support larger masses, what would you have to do? You'd have to move this to the left, the plank to the left. Either that or make the plank heavier. Okay. And if this was a scaffolding and you want to support large weights, then you would have to nail this thing down. Okay. All right. Okay, this problem says a uniform boom shown below weighs 700 newtons. Again, 700 newtons is roughly your weight. So that's the weight of this boom. And the object hanging from its right end is 400 newtons. The boom is supported by a light cable and by a hinge at the wall. Calculate the tension in the cable and the force on the hinge on the boom. Does the force on the hinge act along the boom? Okay, so there's the tension. Okay, there's the weight of the boom. It's a uniform boom, so the weight is, okay, they don't give us the length, so probably you don't need the length. L is, okay. And let's say that there's the reaction force that the wall hinge exerts on the boom. Okay. So here is the boom, an extended object, and there are 4 forces acting on the boom. The tension in the cable, the reaction force, the weight of the boom, the force of gravity, and this force. Okay. And so since the boom is at rest, okay, so what are the 2 equations that need to be satisfied? Sum of the forces should add up to 0. Sum of the torques should add up to 0. Okay, so we'll apply those 2 forces. So calculate the tension in the cable and the force on the hinge and the boom. Okay, now when we want to calculate the tension, we know these 2 forces, we don't know this force. So if you will use this equation and we'll calculate the torque about this point. Why will we calculate the torque about this point? Because that force will be eliminated. And this will be the only unknown. Okay, so that's the smart thing you want to do. Okay, so for the first part, to calculate the tension, we'll use this equation, we'll calculate the torques, and we'll calculate the torque about that point. Okay, so for part A, all right, and now here's another thing we'll do. So there is, and this force, the tension, this is T sine theta, and this is T cosine 45. Okay, so you have to be careful. So now, so we're calculating the torque about this point. There are 4 forces, 1, 2, 3, 4. But these 2 forces have that same variable, okay? The moment arm for this guy is that, okay, what is this distance? The moment arm for that is the length L, and that is L sine 20. This is L sine 20. And this distance is L cosine 20. All right, so that's a counterclock. That force will give you a counterclockwise torque. This force will give you a counterclockwise torque. This will give you a clockwise torque. This will give you a clockwise torque. All right, I'm going to write these guys down. So I'll write T cosine 45 times the moment arm is L sine 20 plus T sine 45, the moment arm is L cosine 20. For this force, that was the moment arm. For this force, that is the moment arm. For this force, this is the moment arm. What is that equal to? L by 2 cosine 20. Okay, so minus 700 times L by 2 cosine 20. And then minus 400 times L cosine 20 equal to 0. All right, L is common. That's why they didn't give you L. Okay, and now you can see that T is the only unknown, and you can solve for that. So what we have is T cosine 45 sine 20 plus sine 45 cosine 20 equal to 350. 700 divided by 2 is 350 cosine 20 plus 400 cosine 20. Okay. So 750 cosine 20. And this is, you know your trigonometry, this is sine A cosine B. I mean sine A plus B, that's the formula for that. Okay. Is sine 65. Okay. Sine A plus B is sine A cosine B plus cosine A sine B. Okay. So the tension okay. So the tension in the cable is okay. Now for part B, what we want to do is calculate the reaction force, and so we'll have to use both these equations. So because you have Rx and Ry, or we could just use Rx and Ry. We can just use this equation. Okay, so let's calculate that. So this is Rx, Ry, okay. X component of the forces, Rx, This guy doesn't have x component, this guy doesn't have, only this, there's this x component. So Rx minus t cosine 45 is 0. Okay. And Ry, so Ry plus t sine 45 should minus these two guys should be equal 0. Plus t sine 45 minus 700 minus 400 equal to 0. This plus this minus of these two is 0. Okay. So Ry works out to that. So R is 550 I plus 550 J. Okay, so what does that tell us? That this is at an angle of, this force is at an angle of 45 degrees, and it's not along the boom. The boom is at 20 degrees. Okay. So the question is, does the force on the hinge act along the boom? And it's not acting, it's acting in this direction. Okay. All right. All right, so here's an old trick that is used. Yeah. When water freezes, its volume increases by 9%. Okay, you guys might have experienced this. If you take that bottle of water and put it in the freezer, completely fill it and put the cap tight and put it in the freezer, it'll bust, of course. Yeah. The forces are tremendous. So in fact, in the old days, I mean, this, you could do this in a stone quarry, and you can only do this where the night temperatures get cold enough for the water to freeze. So let's say here's a mountain and you want to cut off this slab. You make a groove, pour water here, and at night when the water freezes, it'll push that slab apart and break it. Okay. All right, the bulk modulus of water is 9 gigapascals. Okay. When water freezes, its volume increases by 9%. What force per unit area is the water capable of exerting on a container when it freezes? Okay, so let's say you pour water in a container and you freeze it, the water is wanting to expand, so it's applying a force in that direction. And to keep it within the container, you have to, of course, apply an opposite force. Okay. So this is the force that the water is applying. Yeah. Okay, so the bulk modulus of water is force per unit area divided by change in volume divided by volume. Okay, so to keep the water within this container, you're applying this force. That's the stress you're applying, which is equal to the stress that the water is applying. water is capable of exerting on the container. So this is the force you have to apply to keep the water in the container, which is equal and opposite to the force that the water is applying. So F over area equal to negative of B times delta V over V. Okay, to keep the water in ice in the container, you have to reduce the volume by 9%. So this is negative 0.09. This ratio is, so negative B is 9 gigapascals. And that is negative 0.09. Okay, the change in volume, you got to compress it by 9%. So this is 981 into 10 to the 7. Okay, the reason I wrote this like that is this is 1 atmosphere. So the force you have to apply is 8,000 atmospheres. That is a very large pressure. Okay. Most structures would not withstand that. Okay, that bottle is no match for that. Okay. So if you want to, so there are discs that are shock absorbers between the bones, vertebrae in your back. If you want to apply a large shearing force to your disc and damage them, there's stuff like this. A disc between vertebrae in the spine is subjected to a shearing force of 600 newtons. 600 newtons is your weight. Okay. Find its shear deformation using the shear modulus of that. The disc is equivalent to a solid cylinder, 0.7 centimeters high and 4 centimeters in diameter. So 4 centimeters, that much. Okay, so that's how big your disc is. Okay. Okay, so you're going to apply a shearing force like that. And the shearing force is 600 newtons. So this radius is 2 centimeters. And the height is 0.7 centimeters. Okay, so shear modulus is shear stress divided by, okay, so when you apply a force like this, now I'm going to draw a side view. This is delta x, and this is h. How much did the top surface of the disc move relative to the bottom surface? Okay. They want you to find that shear deformation. Okay, or since we have h, we can calculate that. Okay, so delta x over h is force over area. We can calculate delta x. H is 0.7 centimeters, 0.7 into 10 minus 2 meters, force is 600 newtons, and the area is pi r square. R is 2 centimeters divided by 10 to the 9 Newton meters squared. Okay, let's take care of the powers of 10. This point minus 2 kills that, so that becomes 6. That's 10 minus 4 when it comes to the bottom. So this becomes 10 to the 5. Then we'll bring it back up, and that's 10 minus 5. So this is equal to 0.7 times 6 divided by 4 pi times 10 to the minus 5. And everything should work out in meters. Okay. That's a distance. So 3.3 into so the top layer of your disk, which is about that thick, will move relative to the bottom layer that many meters, and 3.33 into 10 minus 3 millimeters. Okay, so you guys know a millimeter is that thin, 3,000th of a millimeter. Okay, so your disk deforms very little. But remember, it's got to last a lifetime. Yeah. What's that?
I was thinking like, wow, it's so easy to damage your back and you gotta keep it for like the rest of your life.
Mm-hmm. Yep. Okay, we'll do one more problem. A suspender rod of a suspension bridge. So we're talking about so one of these guys. So we'll do the numbers for one of these guys. Have any of you guys driven on that bridge in Jacksonville, 9A on 9A? It's a very pretty bridge, you know. So one of those rods. So a suspender rod of a suspension bridge is 25 meters long, which is roughly the width of this room. Yeah. If the rod is made of steel, what must its diameter be so that it does not stretch more than 1 centimeter? So you put a load, the less you want the rod to stretch, the thicker you want it to be, right? And so what are you trying to do? Remember, for a given load, there's the elastic limit. You want the strain to be way less than that, okay? So, and that'll determine the stress. And the force is fixed, so the thicker the rod, the less the stress, okay? So that's what you're trying to do. All right, is 25 meters long. If the rod is made of steel, what must its diameter be so that it does not stretch more than 1 centimeter when 25,000 kg truck passes by it? Assume the rod supports all of the weight of the truck. Okay. So there's the rod. Young's modulus is force over area. And the force, remember, the rod is supporting the weight of the truck. So Young's modulus is mg over, and it's a circular cross section, pi r square. I don't know. So this is in the denominator, we'll leave the pi there, we'll bring the r square over there. So r square is mg over pi All right, so now we can put all the numbers in. What are you supporting? 25,000 kgs, so 2.5 times 10 to the 4 kgs. G is 9.8 meters per second square. The length of the rod is 25 meters pi, and you want it stretching 1 centimeters. And the Young's modulus for steel (20 times 10 to the 10 pascals). Okay. Everything is in SI units. Okay. So what we're going to do is take care of parts of 10. That is 10 to the 11, 10 to the 9, or what? I'll leave the 20 there. 10 to the 10, 10 to the 8, 10 to the 4. That comes to the top. 10 minus 4, square root of that is 10 minus 2. Okay, so R is 10 minus 2 meters, and that's a good thing. 10 minus 2 is meters is a centimeter. Okay, so the answers are coming out in centimeters. 2.5 into 9.8 into 25 divided by pi into 20. Okay. So a rod as long as this room, and you have those rods on the bridge there. Okay. So let's see how much it'll stretch when a truck goes by. Okay, so 3 centimeters, the radius, a little over an inch, so the rod is about that thick. Okay. And of course, to make it stronger, you don't want a straight rod, you want twisted wires, thinner wires, and take a whole bunch of wires and then twist them. Okay, so you got to learn all kinds of tricks. What is the motto? Less material, stronger structures. And so on. Okay.